Here for lecture 15 on the proof complexity as a computational lens course, we're continuing to talk about size-space trade-offs. So let's recap some of what we did last time. We did a lot of things. We had trade-offs between closed space and width and between monomial space and degree. I'm not going to talk about those. We also saw that closed space and width, closed space on the one hand and width and length of the other are totally unrelated. Basically, you can have maximal closed space complexity and minimal complexity with respect to length and width. But the results that we're maybe the most excited about are size-space trade-offs, length-based trade-offs for resolution, and size-space trade-offs for polynomial calculus. And basically, what we did is we just reduced to the question of pebble games. So we saw that if we have strong trade-offs between time and space for pebble games, where we place pebbles on a graph, black and white pebbles corresponding to black pebbles are like deterministic computation steps, white pebbles are non-deterministic computation steps. If we have matching upper bounds for black pebbling and lower bounds for black-white pebbling, then we can translate that to size-space trade-offs in proof complexity. In fact, the results are slightly stronger than what I told you. Resolution can even simulate sometimes black-white pebbling if it's not too white. So resolution we don't know if actually resolution could simulate any black-white pebbling, but we know that there are some settings where black-white pebbling beats black-white pebbling and where resolution can match the black-white pebbling results on time and space. And basically for resolution, we had an extremely tight correspondence. So we got exactly the same results up to small constant factors. For polynomial calculus, we needed to do a restriction argument. So we had a logarithmic factor loss, which is really annoying. I wanted to state two example theorems just to remind us what these theorems look like in two different space regimes. So one space regime, we realized, this is an open question in proof complexity, but for pebbling in constant space, you cannot expect to get super polynomial pebbling time. Just by counting arguments, if you're using a constant amount of space in pebbling, then space S, say, then there's n choose S different pebble configurations. They don't need to repeat. So n to the S is a worst case pebbling time. We know that this is tight. And you can translate this also into proof complexity trade-offs. As soon as you pick any non-constant space, you go into the super polynomial regime. So that there are formulas, pick your favorite slowly growing function g of n, and we can come up with 6 CNF formulas explicitly constructible, like we can write them down, that are refutable in very small total space in resolution, so essentially g of n. They have linear size or linear length even proofs in much larger total space, so essentially third root of n over gn n over gn squared, but gn is like very, very small. So you should almost think of this as n to the 1/3, not quite. But if you try to shave anything off this exponent, like if you manage to get the exponent 1/3 minus epsilon, then this pushes the size up to super polynomial. And what happens, the upper bounds are the same for polynomial calculus, even without dual variables, so PC. And here you also get the matching lower bounds for PC. Here, what you need to do is, again, for the lower bound, we need to sneak in a log n factor, and the lower bound holds even with dual variable for PC. If you're interested in the other extreme of the spectrum, so exponential space, then we can get results such that, again, explicitly constructible 6 CNF formulas, where the of linear length, I should have said linear length, so that the total space of refuting them is Noticeable, but not too bad. Something like n to the 1 over 11, say. So polynomial, but not too bad. And there are refutations in size, again, linear, which you get from the Hebling formula, and the total space will be something like n to the not 3 over 11. So like they're a factor, an exponent 3 apart. And then you say that if it holds that the space of any refutation is less than n to the 2 over 11. So even if you try to, you're nowhere close, you're like a square above what you know you can do. But this forces the size to be actually exponential. The size is going to be n to the 1 over 11 factorial. And again, what happens? The upper bounds hold for both resolution and PC. And the short refutation is both for resolution and PC. Polynomial calculus without dual variables. This lower bounds holds only for resolution. And what happens in PCR is that you need to divide by something like 10 log n to get the PCR space. And this means that also I stated even sharper trade-offs at all the way up to space n log n, n over log n, for resolution that you get from the very best results for black-white pebbling. For those, we sort of don't get anything in polynomial calculus any longer, because then the log that we pick up of the proof size is so large that we lose. Okay, so, and the way we got this is by looking at pebbling games, but actually the core of this was not about pebbling at all. It was just that we took, we had trade-offs between length and a very weak measure, namely we just looked at variable space, number of variables mentioned in any configuration. And then we argue that if we did substitution with the right gadgets, then we could lift that to trade-offs between length and closed space in resolution. And we just, the reason pebbling formulas were useful is that, well, they exhibit this kind of trade-off between length and variable space. But if you could find me some other formulas that have trade-off between length and variable space, then I would happily plug them in and see what we get. So it just so happens that I personally don't know any other way of getting such formulas, except for looking at pebbling formulas. But note that it's a very mild trade-off. You're just saying that if the length has to be small, then the number of variables has to be somewhat large. But we know that for these formulas, you can actually get them, you can refute them in constant closed space and everything. So they're like super easy with respect to closed space. So we just need this very, very weak trade-off, and then we do a substitution, and we do a lifting argument and a simulation argument, and then we get very strong trade-offs between length and closed space. And then what we needed to do, so this was why we got so tight results for resolution. what did we need to do for polynomial calculus? For polynomial calculus, we used two things. One observation was that variable space is the same as for resolution. And in fact, this is very general, like any implicational proof system, any sequential implicational proof system. Sequential proof system, the proof consists of lines. Implicational, every line is actually semantically implied by previous lines. Any semantic implicational proof system, in any such proof system, variable space is lower bounded by resolution variable space. And if your proof system is strong enough to simulate resolution with respect to variable space, then which most proof systems are, then variable space is the same measure. Except, okay, for algebraic proof systems, now we have to decide whether x and not x are different variables or not. If they are different variables, then obviously there's a factor 2, right? But other than that, so for starting with the resolution and all the way up to Frege, variable space is the same measure, which is kind of an interesting property. The only, I think, complexity measure in proof complexity that we know of that has this nice property. Note that as soon as you have extension rules, then you can, a line that introduces a new variable that means something, that is no longer an implication. So extended Frege is not implicational. Extended resolution is not implicational. So then variable space is different. But for all the standard like resolution, polynomial calculus, cutting planes, under the Frege, variable space is the same. So in particular, the same thing that held for resolution with respect to space held for polynomial calculus. And then we needed to use a restriction argument. And what we did is we lifted with a very particular gadget, binary XOR. And then we used that for binary XOR, there's a very nice restriction, namely for every pair of variables, pick one of them and set it to a random value. Now you get your original formula back, except for renaming variables and maybe flipping signs. But now all, in a resolution proof, all high width clauses have disappeared because of the effect of the random restriction. For polynomial calculus, all high degree monomials also disappear with high probability. Except that the log factor loss comes from that you have to make this random restriction argument. So two open problems that I already mentioned, kind of. Are there other formulas for which we could get trade-offs between length and variable space and get nice results? Second question, and I thought about this for several years and then gave up, but I really think it's time to crack this. Can we prove exactly the same type trade-offs for polynomial calculus as for resolution? Or if not, there should be a good reason. Like you should either prove that black-white pebbling and polynomial calculus have the same type correspondence as black-white pebbling and resolution has, or prove that this is not true. I think this should be doable. Only problem, if I knew how to do it, I would have done. There was one more thing that is worth talking about. So the upper bounds, in these theorems are A and B. They are for the standard proof system. So therefore, total space. And for the standard syntactic proof system, where in resolution, you have the resolution rule. In polynomial calculus, you can take linear combination and you can multiply. The lower bounds, just looking at what we did, firstly, we got clause space or monomial space, which is a much stronger measure. And often they were, for resolution, they matched exactly up to constant factor. Again, for polynomial calculus, not quite, but again, still, I mean, total space and monomial space almost matching. And more interestingly, if you looked at how the lower bounds worked, they worked in a semantic proof system. Because we never charged for inference step. Like, whenever you did it, so somehow, if you think about it, the way we did our lower bounds, whenever whenever someone did an inference step, we just said, yeah, we don't need to analyze that because the implications don't change. We were only interested in when the implication of what we had on the board changed in such a way that it was not when the implied, like the semantic content of the configuration on the board, when it got stronger. When it got weaker, we also didn't worry because, you know, dealing with weakening is not a problem. We did worry about the only time that we really had to work hard was when someone downloaded an axiom. Except for that, we didn't care. So these trade-offs actually we got between number of axiom downloads in variable space. And that is, so this means that if you think about this upper bound in an exponential regime here, this lower bound holds even for a proof that has a polynomial number of clauses in memory. And in a single shot, can anything that is implied by a clause set of this fairly big size, anything that is implied, even if it's like a pigeonhole style consequence that would take an exponential number of steps to derive, you can have it in a single step. Even in this very strong setting, we get matching lower bounds. Okay, when you write the paper, you obviously emphasize that this is a very strong aspect of the technique. Like we get tightly matching upper and lower bounds, where the upper bounds are strictly syntactic, standard kosher proof system, and the lower bounds are where basically inferences are free. Amazing. But this is also weakness if you think about it, because in a semantic proof system, the problem is that you can do anything, any clause, any formula Fn is refutable in pretty much linear size and linear space simultaneously. Because note that the exponential lower bounds on length no longer apply. I can just download the whole formula, that's linear space. Now I can stare at it and say that, well, the empty clause is implied, so I can have it in a single step. That's linear space, linear size. So this means that what we did last time cannot possibly give us anything in the superlinear regime. And this is also true for, if you look at time-space trade-offs have been studied in a number of different settings for pebble games, been studied for Turing machines and for other intermediate models. And typically you get something like schematically, the kind of trade-offs you get is something like space times time is n squared, where n is the formula size. And then you say, oh, so this means that if you push space down beyond linear, then you could push time up to, you know, best case, maybe quadratic if you can do constant space. And there are pebbling graphs that have exactly this property where we get these type of length closed space trade-offs that are tightly matching along the whole curve. Then there are other stronger trade-offs which look something like, okay, space times log of time is maybe linear, or maybe I lose a little bit, so maybe I have n squared or n to the delta, or you know, something. And that sort of tells you again, actually, let me go back to the end here. So this tells you again that well, if space is now square root n, then actually you see that the time or the size, if you're doing proof complexity, has to be exponential actually. Okay, but again, for linear space, we don't get anything. And of course, if I have a delta, which is here like a half or something, then even for, as soon as space hits n to the delta, there are no consequences. Am I making sense? So the question we asked last time is the following. So suppose that a formula F is refutable in size or for resolution length, but I'm kind of relaxed, as you noticed. I've defined the same size and length for resolution to be the same. So suppose a formula F is refutable in length or size L. Does that mean that F can also be refuted note that we always know that you can do it in linear closed space or line space or monomial space or whatever you call your measure. So can we refute the formula in space at most linear, which you can do in resolution and any reasonable proof system that simulates resolution, without paying too much in the proof size? Say I'm willing to go to polynomial. It's a very reasonable question. Like suppose I promise to you that there is a refutation in size L. We know that linear space is always enough. And now I'm just asking you, could you please do linear space? I understand maybe you can't hit L exactly, but big O of L would be great, or maybe L squared, or L to the 10. I'll be generous. Any constant factor you can think of. Is this always possible? Okay, this was one of the open questions that we had last time. And what I have said so far is we don't know yet. We'll know soon. But what we do know is that what we did last time inherently is completely unable to answer this question. Okay? So the answer to this then has to come by other techniques. It turns out that the answer is no in a very strong sense. And there's a paper by Beame, Beck, and Impagliazzo that they did in 2012 and then a journal version in 2016. They give very strong trade-offs for regular resolution. And they actually first got the results for regular resolution. And again, I don't know if you remember that I said before that sometimes some of these proof complexity results, you get your results for regular resolution first because it's easier. And although we know that regular resolution is exponentially weaker for most formulas, it shouldn't be. So once you've sort of nailed the regular resolution lower bound, unless you're really, really using regular resolution in some non-trivial way, the same thing should kind of hold for general resolution. So they were able to get results also for fully general resolution, but with much worse parameters. Okay, and then, so this was Beck, Beame, and Impagliazzo, Chris Beck, and then Chris Beck was visiting, or we met in Banff actually, and then he came to Stockholm, and we continued to work together with Tang, who was visiting from Tsinghua. And then we got it for resolution with better parameters and polynomial calculus resolution. And again, showing that no, basically morally, we're going to say something like that. There are formulas. The way you should think of this is not quite what we're going to prove, but sort of there are formulas refutable in large polynomial length, say like maybe n to the 10. We're not going to get these big parameters, but just so you get a sense. Like maybe the proof size is like n to the 10, but the space is also going to be roughly n to the 10 or maybe n to the 8. So like you really need to keep most of the proof in memory. And if I want to go down from space, I'm saying, okay, could you at least, I don't know, I'm not asking for linear space, but could you at least go down from, n to the 8 to n to the 4, maybe, where n is the formula size? And then the answer is no. Then this proof size blows up from n to the 10 to super polynomial. Okay, and we're gonna look at the result for resolution, and we're going to look at the simplified proof that we did. Most of the heavy lifting was done by Beame, Beck, and Impagliazzo, and then we just identified some places in the proof where you didn't have to suffer so much. And maybe I'll get to say what the difference is. So what this will give us, so let me state what we're going to prove just to get a sense of the parameters. I should say that the parameters, there are several open questions regarding this, which I think are excellent. One is the parameters for regular resolution are much better. Could we, if we just work a little bit harder, could we get the regular resolution proof to work. The polynomial calculus proof is very, very complicated. It only holds for fields of characteristic distinct from 2. It would be nice to get a similar kind of trade-off that is not dependent on the field characteristic. These are, and also, yeah, I think there are lots of room for improvement here that would be interesting. So this is the third theorem that I'm stating today. So let me write it down. So there is a fix W to be a function of n. Let it be, actually, let me insist on that it's somewhere between 4. W of n is at least some constant 4. It's at most the 4th root of n. Then there exist, again, fully explicit, you'll see them, 8 CNF formulas. So formulas of constant size k for k equals 8. Yet another problem, bring that k down from 8 to 3. That should be doable. And it would be nice to do. So there are formulas of size theta of n such that. So what do we get? That there exists refutations in closed space closed space is going to be W log n. You should think of W is a fairly small parameter and log n is logarithmic in the formula size. And the length is exponential in this. But again, you should think of this. We'll talk about parameters later, but you should think of this as, maybe this is going to be log square or something. So it's quasi polynomial in the most interesting setting of parameters. And this holds in resolution. So this is a small space refutation, but in large length. There are also refutations, other refutations, where you can do length polynomial. So n to the big O of 1 for some constant times, well, exponential in W, but if you pick W to be at most logarithmic, that's going to be polynomial. And now the space is, but now the space is bad. The space now is going to be exponential in W. Plus potentially some constant in n. So in particular, you should now think of this as probably super linear space. And this is again in resolution. Note that both upper bounds are for resolution. So in particular, polynomial calculus can also do this. And now the trade-off says that for any PCR refutation, assuming that the characteristic of the field we're working in is not 2. Then, if you look at the proof size, it's going to be exponential in this W parameter that we'll talk about in a bit, divided by the monomial space, raised to the power of, and here is where there's really room for improvement, log n over log n. And let's throw in some constant factors. Okay, I'll let you stare at this for a few seconds while I just make them room here. So the point is, what happens now that if the monomial space is significantly smaller than exponential in W, then you're going to pick up some polynomial factor here. Okay, so there's some n to the delta here, and here you have a super constant exponent. So it's like n to the delta times. Admittedly, it's like it's not blowing us away. Log n over log n is like not the most amazing lower bound, and it should be possible to do better. And again, for regular resolution, they get something much better. But it's definitely super polynomial. And I think the most interesting setting of parameters here is to say something like W should be k log n for some pretty large k. Okay. Because then, you see, then the length here, the short refutation is basically going to be dominated here. Then we're going to pick up exponential in k log n, that's going to be n to the k. So the proof size is going to be n to the k. But again, you see that the space, as I told you, the space will also be n to the k. So we have a somewhat short proof. You know, it's not exactly the same exponent. So I said n to the 10, n to the 8, something like this, right? So, but essentially, except for this constant exponent factor in n, the length and the space of the short refutation are essentially the same. And now you say, but you say in that setting, you say that actually the closed space complexity is amazing. It's very simple with respect to space. Log square. Log square is by any standard very small space. And we think of this as polylogarithmic. It's like that's easy with respect to space. So it has short refutations, it has space-efficient refutations. But now, again, the way you should think about this is suppose that you can shave like a large factor of n to the k in the space. Well, then you're going to have n to the k here. Here you're going to have, say, n to the k halves or something. Obviously, we're hiding a little bit in the constant factors that I'm cheating you on. Pretend that there are no asymptotics here. And so suppose that this is like n to the k and this is n to the k halves. Then you would n to the k divided by n to the k halves would be n to the k halves raised to a non-constant factor, which is what I promised. Okay, and again, the open problem, improve these parameters, try to get it closer to regular resolution, try to do it for independent, for polynomial calculus. I'd like to get something that is independent of the characters. And I should have said, yeah, so this is from the Beck, Nordström, Tang 2013 paper, but relying heavily for like the technical insights on Beame, Beck, and Impagliazzo. Questions so far? Is it clear what I'm saying? So this is a fairly technical result. So we have had, so far in the course, I think we have basically 3 different types of lectures, maybe. Some lectures where we arguably did everything, or pretty much everything, except for the first lecture, for the pigeonhole principal lower bound, for the Tang lower bound, we didn't do the concentration of measure calculations, but they're standard. Like, and other than that, and I didn't show maybe that you got truly independent bit when you sampled on an affine subspace, but it was highly believable. So like we didn't cheat you on any technical DT3. Okay, and then the second type of lectures was what we had, for instance, last time when I did some of the easy part. We said that if you do a substitution, then we define this projection operator. Then I said that whenever you run a proof on the substituted formula, it projects down to a proof on the base formula. And I didn't do this proof, but it's the kind of thing that it's mostly annoying. You sit down, I promise you, like, I'll give you 1 or 2 hours and some coffee or tea, and you'd like work it out. You have to be a little bit careful in your calculations, but there's nothing. It's work. It's not trivial, but it's not like hard. The hard thing was, okay, when is this projection space preserving? And that proof we honestly did, right? Now the third category of proof is what we're going to see today, where I think to do this properly, we would need at least 2 lectures, but we only set aside 1. So I'm going to walk you through the proofs. I'm going to give you some highlights. There's going to be lots of intuition. And if the intuition is too bad, I hope that you will help me by asking so that I can provide better intuition. Hopefully, I'll try to do some of the proofs, but I won't talk about polynomial calculus at all. Okay? We're just going to focus on resolution. That's hard enough. And I'm not going to get these parameters. So if all ends well, at the end of the lecture, we will have a non-trivial size-space trade-offs obtained with the right technique. And then I'll maybe say something brief about how you will optimize. Okay, does this make sense? Yeah, I guess I'll elaborate it in a bit, but just to stress that the answer to this question is no in a very strong sense. And this means that all the questions that we asked last time about trade-offs were answered with a no. So far what we have seen is that for most pairs of proof complexity measures, you cannot optimize simultaneously. If you're a complexity theorist, then you would maybe say, yeah, what did you expect? I mean, we have a negative outlook on life. If something is hard, it's usually hard. But it's one thing believing it. I mean, we believe a lot of things. We also believe that P is distinct from NP and things. That the nice thing here is that we're looking at weak enough computational models that we can actually get these separated unconditionally and they're very explicitly. And I think that's nice. So how are we going to get these trade-offs? We will visit an old acquaintance, Satan formulas, or Satan contradictions. So let's recall what Satan contradictions are. Recall that we have a graph throughout these lectures, a graph with vertices v, edges e. We have a charge function that maps every vertex to 0 or 1. And we are interested in odd charge functions. What are odd charge functions? They are functions such that when I sum up all the charges over all the edges, I get an odd number. And Satan formulas are basically for every vertex, I write down in the CNF encoding the parity constraint that says basically that for a vertex, look at all the edges that are incident to that vertex. I identify the edges with variables. Every edge E I identify with X sub E. Sometimes when I'm lazy, I'm just going to use E to overload notation and refer to the variable as E, but I'm not lazy yet. So the parity constraint for vertex V says that summing up all the edges, the number of true edges has the same parity as the label. And then we saw when we did the Satan contradiction that how are you going to do this? Well, you're just going to expand it out in the simplest way that if the graph has bounded degree D, then these are going to be, every constraint is going to be a DCNF formula over 2 to the D minus 1 clauses. I'm not going to type that out again. And the Satan formula is that assuming that we agree that you can write some CNF encoding of this, then the Satan formula over G with charge function chi is just taking a and over all vertices of the parity constraints for the vertices. And now by a simple counting argument, supposing that G is a connected graph, this formula is unsatisfiable if and only if the charge function is odd. And in fact, something that we won't really use, but we don't really care about what charge function you use. I only care about the whether it's odd or even charge. And I think we did this in the second lecture. You can even like very formally, any two odd charge functions, you can go from one to the other by just flipping polarities of variables. So they're really the same. So without loss of generality, so jumping ahead a little bit, we're going to look at so-called grid graphs that look like this. And I'm not going to talk about the charge function. Let's just agree that the top left vertex has charge 1 and all the other vertices have charge 0. If you would have preferred another charge, like you can have it and then we can relabel and just negate literals as needed. Doesn't really matter. And this means also that later when we're gonna hit these formula with restrictions, then of course the charge is gonna change, but somehow I'm mostly gonna pretend that it's still the same charge function. Because it really doesn't matter. I could whenever it matters, I just relabel. Or relabel inside my head so that I say X, but actually I meant not X. Like in a very formal sense. So what did we know? We know already that if G is an expander, then this Saking formula is exponentially hard for resolution. We didn't prove, but I told you this is one of the results, one of the main omissions so far in the course. Also for polynomial calculus in fields of characteristic distinct from 2, it's exponentially hard. This requires a proof. Note that all the polynomial calculus lower bounds that we did were oblivious to the field. Here, this lower bound for Saking will obviously only hold in characteristic distinct from 2, because in characteristic 2, you would just sum up all of these parity constraints and the characteristic of the field will help you because it does odd even counting. And this requires different techniques that we are not covering in this course. We'd be happy to do it some other time. We can talk about. Okay, this is great, but not so great for us because we want trade-offs. We're not going to get any trade-offs from expanders. They're just hard, period. So we need to think a little bit about how we're going to get Saking formulas that are not too hard. And what we're going to do is we're going to look at long, skinny grids. We're going to have W rows, where W is a small number. And then we're going to have L columns. So the length of the grid is going to be large, and the width of the grid, if you wish, is going to be very small. W is the same W as over here. N is now a little bit overloaded. Actually, N is going to be L times W. So you have to do some. Basically, I'm going to avoid saying N from now on, and I'm just going to work on L and W. But you should think of, when you're thinking of how these parameters relate, you could think of, we know that W being logarithmic in L is going to be an interesting parameter regime. So we don't have to commit to that, but definitely I want it to be growing with. I want W to be growing with log L, but I don't want it to be too large. So it's going to be like at most the 4th root of L or something like this. And now, again, we talked about the odd charge function. So I take that Saking formula over these Saking formula over these graphs. And now I want to prove my time space trade-offs. Are we happy so far? Actually, while you're thinking about whether you're happy, let me extend the grid a little bit more. Just because it's going to be easier for us. One other thing you could think about is I want you to find efficient refutations of this formula. Space efficient and time efficient. size efficient. So this is another thing to think about. Which one are we going to do first? We need a very space efficient and a very time efficient refutation of these formula. Some in the audience are not allowed to answer. So the first thing we're going to use is something that we didn't talk about so much is depth. What is depth? The depth of a proof is the length of a longest path. And now we're going to use heavily, like suppose I give you any resolution refutation and I gave you a lower bound of the depth. What happens to the depth if I now, I take the proof tag and anytime you use a clause twice, I rederive it from scratch. In other words, I make the proof tree-like. This we know can blow up the length terribly, exponentially. What happens to the depth? Nothing. It doesn't change, right? So in fact, so if a formula is refutable in depth D, then what I'm saying is that there's actually like basically a depth G binary tree proof tag kind of refutation. Are you with me? Okay, let's just so good. So then we prove the next proposition. Let's just have it for the record because I'm not sure if we ever said this explicitly. So if F is refutable in resolution, we're in resolution all day today. If it is refutable in depth D, then F is also refutable simultaneously, meaning there is a resolution refutation that achieves both of these parameters in length. And I should say in tree-like resolution even. In length, well, just look at the binary tree and the number of nodes is going to be basically, unless I'm screwing up, 2 to the d plus 1 minus 1. And I claim that we're going to be able to do clause space d plus 2. Okay, how are we going to do this? Well, let's look at the proof tag. Suppose it's not a full binary tree. Well, that's only making your life easier, actually. And I think we talked about that. In fact, like if you allow yourself to use weakening, which you can do because it doesn't really change the space, you can get a full binary tree. But otherwise, what I'm going to show you now is also going to work if the tree happens not to be full. Well, now you just look at this. This is a proof tag. And we know we talked about these configurations and downloading and inferring clauses. It's just a black pebbling. So you just pebble this tree, right? So you use three pebbles, so clause base 3 to derive this clause, then you save it. And now you use clause base 3 to get this one, total clause base 4. Then you erase. And you take these two and infer this clause by resolution, and now you erase. And now we know that you can infer this clause in clause base 4. Keeping this in memory gives clause base 5. And then you continue, right? So this is how you get this. And note that I'm only touching every node in the binary tree once. So it's a tree-like refutation. Okay, but this means that all I need to do is to come up with a somewhat shallow refutation in tree-like. And I can think about tree-like resolution. And now tree-like resolution, as we talked about, is really the same as decision trees. So what does this mean? So I can just think about the decision tree that queries edges in my graph. And if I can come up with a, just looking at what the space efficient, where do we have the space efficient refutation? Basically, in order to prove this, if I can get a decision tree that queries at most W times log n edges and then decides where the violation is, then by this proposition, I immediately have my space efficient refutation. Am I making sense? Okay, so now we just need an efficient decision tree. From now on, we're going to fix. Yeah, I'm going to erase it soon, but whenever from now on, unless I'm telling you something else, G is a W by L rectangular grid. I didn't tell you what the edges are, but you can sort of tell from this picture, right? You index, we can think of every vertex as being indexed by its row and its column. And basically, if you're ij, so vertex ij has edges to, let's see if I can say this without screwing up. Keeping the same row, I can take j plus minus 1, right? This is going in this direction or this direction. And then I can keep the column the same and just go up or go down one row. So there will be edges also to I plus minus 1 j. And then you can think about what am I going to do in the topmost and the bottommost row. Should I wrap over or things like this? Or should I make a torus so that it wraps around also horizontally? It really isn't important for this result. Everything I do would work for any, pick your favorite. If you want to work on a torus, long narrow torus, you can do that. We're going to pick up a 2 somewhere in the constants, but, not good. The nice thing with working on a torus is that you'd get a 4 CNF. Now we're going to have some 2 CNF clauses here. And if you're worried about this, then, make it into a torus, but I think this looks nicer and it's going to make the proof a little bit nicer. Okay, so from now on, G is this rectangular grid, and we also agreed on that the charge is 0, except the top left vertex has charge 1, right? Just writing down on the board what you and I already agreed about. So now my next proposition says that for G, this W by L grid, the Zeitian formula can be refutable, it is refutable in depth big O of W log L. Okay? And maybe you've already seen how to do this, and I apologize for boring you to death. But what are we going to do? Well, basically, I'm going to query all of these edges. Note that I just query all of these edges. If I pick up a 1, then both of these charges flip to 1. If I pick up a 0, nothing changes. Suppose I pick up a 1 again, then again, both of these charges flip. And then I pick up a 1 or 0 here. Suppose I get 1, 0, 1, 0. Then basically, nothing much has changed. And now note that I've actually disconnected this graph. And since I said that we picked it 2 odd and 2 even, we now have 2 disconnected components, and this is the odd charge component. And this is the even charge component. Right? Or, if I picked up some other, the point is I just cut the graph in half. And after having picked up these values, I just check where did the odd charge go. Okay, suppose it went here. Well, now I'm obviously going to do binary search. So I'm going to ask about these. Or, again, disconnecting the graph. And now suppose that I actually picked up 1, 1, say, and all the others were zeros. So now actually this flipped into an even charge. And the odd charge resides over here. And now I'm just going to keep on doing binary search, the graph shrinks in halves every time. And after at most a logarithmic number of recursions, I have actually isolated a violated vertex. Are you happy with this? So let's just see. So number of recursive calls are going to be the 2 logarithm of L, rounded up if you insist, I guess. And we do exactly W queries per recursive call. And then finally, I will have, I mean, when I have a small odd charge component and I query all the edges in that odd charge component, then, I mean, the odd charge has nowhere to go. There will be a violated vertex. Are we happy with this? Okay. So now we need to figure out what the short refutation would be. Interestingly, okay, a side remark while I'm cleaning the board. Suppose that you set W to some small constant, W like, 4 or 5 or something like this. Then actually the proof is not too large, right? So if you're evil, you generate Satin formulas over long skinny grids and you send them to the SAT competition. What happens? These are easy formulas, right? They have short resolution proofs. So, will SAT solvers find these proofs? No, they won't. Or at least back in 20. Okay, SAT solvers that happen to run Gaussian elimination will, and they will kill these formulas. But typically you don't run with Gaussian elimination because in the SAT competition you have proof logging, and the standard proof logging systems are based on resolution, and you can't do parity reasoning conveniently, so you switch your Gaussian elimination off. Still, but even without Gaussian elimination, there's still a short resolution proof. But somehow the Satin formulas screw up your standard good heuristics, so the SAT solvers perform terribly on these formulas. Or at least they did a few years back. It might be fun to change again, to check again, but like it really didn't. Okay, so we need to come up with some space diffusion proof. So what I'm going to do is the following. Suppose F is unsatisfiable. Pick some variable x and let Cx be all clauses containing the literal x. Let Cx bar be all clauses containing x bar, and maybe, I don't know, let me write f minus x to be the rest. And let me, I'm inventing some notation on the fly. Let me write Cx bow tie C not x to be the set of all pairwise resolvents. Of clauses here and here, except that there could be a lot of trivial ones, and let me throw them away. Okay. Then I claim that in fact f minus x union Cx bow tie C not x is also unsatisfied. Okay. This gives rise to something that is called variable elimination, or in proof complexity is known as Davis-Putnam resolution. Fix a variable order and just resolve away the variables in that order. This, when you're done, you are basically, I mean, when you end, you have a formula with 0 variables. And you know that if you started with something unsatisfiable, your final formula with 0 variables is also unsatisfiable. How many formulas with 0 variables that are unsatisfiable do we have? One, it contains the empty clause. Okay, so this is going to be a refutation. Am I making sense? In general, is this a great idea? Not clear. I mean, this could actually have exponential size and exponential space. Okay. But what I'm going to do now is let me start by just resolving. Let me order the variables by column and then from top to bottom in every column. I'll start by eliminating this variable. Then I will take all clauses talking about this constraint, this vertex, and all clauses talking about this vertex. And I'm going to pick up a bunch of clauses over this edge and this edge and this edge. Right? Next, I download all the clauses that encode the constraint over here. And now I eliminate this edge. And I'm going to get a bunch of clauses that mention these variables. Next, I download all the clauses for this constraint. So I'll get rid of, and now I resolve over this edge. And then I pick up this. So let me see now just what happens. Suppose now that I download all the constraints for this clause. Then I can now get rid of this edge. I resolve it away. And I pick up these two variables. You see now that I have a cut in the graph. And then I download this and get rid of, actually now I'm going to resolve away this variable first, say, and then this variable. And what am I going to pick up? I'm going to pick up this and this variable. It's kind of clear that I can do this. Now, what is the length of this and what is the space of this? I'm doing proof by picture. Well, if you think about it, first, when I downloaded all these constraints, I just had that the parity here is off. Then when I download both of these, then I just basically, what I'm going to say is that the parity of this cut has to be off. And then when I download these and resolve, I say that the parity of this cut has to be off. And what I'm doing right here, I'm just carrying along the parity of this cut. But even if you don't care about this, I'm going to have clauses over these variables. Suppose you don't like, you're not buying that it's the parity maybe, but it's clearly all my clauses are going to be over these variables. How many variables are there? At most. W plus 1. Okay. How many clauses could I possibly have here over W plus 1 variables? 2 to the W plus 1. Okay, 4 if you're like unsure, or 3 maybe, but in fact, you're gonna, in this case, all clauses are gonna be over all variables. So then it's really gonna be 2 to the W plus 1, worst case. Right, worst case, I mean, clearly worst case is 2 to the big O of W. But it's like, it's really like, it's gonna be actually 2 to the, it's gonna be 2 to the W plus 1 minus 1. So it's gonna be 2 to the W. So this refutation, the space at all times, the clause space, is going to be 2 to the W. Okay. How much, and now I download the vertex constraints one at a time. And the operation that really takes time is to do this operation. But that's going to be, so how many constraints do I have here? Also essentially 2 to the W. So I will need to resolve 2 to the W clauses with 2 to the W clauses, worst case. So it's going to be 2 to the 2W. So per parity constraint, per parity constraint, we get something like 2 to the 2W resolution steps at most. Okay. How many parity constraints do we have? L times W, right? So now we will actually, now you see that the length is indeed, and L to the W is N. So this is definitely N. This is polynomial in N, and here you have the exponential in W. So we're matching the length, and we're matching the space. Okay. So good. So now the question is, of course, is these are only upper bounds. It's not so clear. I mean, proving that this is tight is another matter entirely. And in fact, we're not able to prove that this is tight, but we're going to be able to prove something. So I think what I propose to do now is let me tell you our plan, and then we'll have a break. Okay. And the trade-off plan is basically we're going to copy Beame Impagliazzo, and they in turn hit the time-space trade-off literature really hard, and extracted the following approach, if you will, for proving time-space trade-offs. So in general, when you look at time-space trade-offs, you formalize some kind of notion of progress of the computation. That measures how far we have got. Except our computation is a proof, so we're going, or refutation. So we're going to look at proofs, we're going to look at refutations, and we're going to measure how well we've done so far. By the way, do you remember anything? Have you seen progress measures before? We did see a progress measure for Tzikin, actually, if you remember. Turns out to be a good progress measure. I'll remind you after the break, because this is the measure that we're going to use. And now we divide. Next step in the approach is that you divide the computation into a bunch of equal-sized epochs. So the way to think about this, let me get rid of it now, and maybe draw it down here. So here is our proof. And I'm going to think of like this as being the whole length of the proof. Then I'm going to chunk it up into a bunch of epochs, like epoch 1, epoch 2, 1, 2, 3, up to epoch n of equal size. Again, we're not thinking about computations, we're thinking about proofs. So we're going to take the resolution proofs and just cut it into segments. When we're thinking now, importantly, we're thinking of the resolution proof as a configuration style proof. So at every time, what you have here is like the clauses in memory at this point. Okay? And then at some point, I just say, I cut at step 100, and we see what are the clauses in memory at time 100. And then at time 200 and time 300, they just cut up to, maybe the proof ends after 1,000 steps. And then I maybe have like 10 epochs of 100 clauses each, except that I carry around the configurations. Okay? And then once we have this, how many epochs? That's going to be a parameter. So now we want to prove something like the following. If the epochs are small, then there's no time to make progress. There is not too much progress within an epoch, because there's just not time to make enough of it. Okay, so like you could, if the epochs are short, it's not like suddenly there during one epoch you basically do all the work. Like I did 95% of the proof happen here. No, that can't be because the epoch was too short. So you're saying if the epochs are really short, then you have to make only gradual progress. Okay? But now the problem is that if the space is small, then it's not the case that you can carry a lot of progress over from one epoch to the next. So basically what I'm saying, and this is similar to other results in somewhat reminiscent, even when you have like, when you're proving lower bound for space-bounded algorithms in streaming, for instance, and so on. Like, if I look at the borderline, at the breakpoint between two epochs, since the memory here is very small, like maybe I did super clever things in epoch 2, but the only thing I'm saving from this epoch, the only thing I remember from this epoch is what is in memory here, right? Because at this point, afterwards, I only have access to these clauses here, plus the original formula. If you did a lot of clever stuff inside this epoch, that's gone. I mean, I only remember what exactly I have in memory at this point. Am I making sense? This is why we're carrying around the configuration. Okay, but now, so we're saying that if the epochs are small, basically if the proof is short and you cut it up into many epochs, then the epochs will be small. And if the space is small, then you cannot carry a lot of progress in between epochs. But now we're saying that, well, to refute the formula, you need to make a lot of progress. Right? Suppose I can prove this where we don't have any parameters, but it stands to reason then that if I'm able to prove this in some sense, then it follows that a refutation that is, or let me say that a derivation that is too short and has too little space cannot refute the formula. At a very high level, this is what we want to do. So far, we did not do anything really hard. I mean, I did do these, the space efficient and the time size efficient proofs. I did do that quickly, but again, I'm not cheating you on anything. You know, maybe if you just sit down and sort of work it out, you could even, like the short proof, maybe the easiest way, you can actually do the proof very explicitly, like resolve over these variables and just see what you get, right? And you can sort of very clearly see for yourself. There's nothing strange. And also the space efficient proof, right, technically speaking, I guess you can build a decision tree and then see sort of what the resolution proof looks like, or you can just trust that, well, I know that decision trees and tree-like resolution are the same. But how to implement this is far from unclear. And note that we know now that somehow we cannot be semantic. Like we have to be very, very syntactic, because again, in the model of resolution that we had on Tuesday, this is just inherently not going to work. You could not possibly get a result like this. So somehow we we can't just say, oh, it follows, this is implied, blah, blah, blah. Like, we really need to look at syntactic clauses and how they are being resolved. Otherwise, there's no hope. Okay, is this a good place to take a break? So before we hit the pause button, are there any questions anywhere? Or from Copenhagen or anywhere else? Good, then let's have a break. We are back after the break. We want to prove size-space trade-offs for Satin formulas over long, narrow grids. Here they are. They have W rows. They have L columns, where we think of L as much larger than W. But W is at least the logarithm of L, and it is at most the fourth root of L. Since L is growing, whenever it's convenient to assume that W is larger than something, say 2, say 4, I'm just going to throw that in because it's eventually going to be true when I mean, we want these graphs to go to infinity in size, and since W is bounded by L, L has to go to infinity, and therefore W will also go to infinity. So whenever it's convenient, again, that W is larger than a constant, we'll just let it be larger than a constant. And this is the formula for which I want to argue my time-space trade-off, except this is another open problem. It should actually be possible to prove the lower bound, the trade-offs for this formula. But notice that I said we were going to have an 8 CNF formula. This yields a 4 CNF. So I can't, the proof I'm going to do today does not work for this formula. Instead, what we're going to do is we're going to take this formula and just do binary XOR substitution. Or, if you wish, that if you think of what XOR is doing, it's actually just taking every edge and adding a copy. So you get a multigraph that looks like this. And then, just as we did for our PCR size-space trade-off last time, what we're going to do is we're just going to hit this with a random restriction that removes one edge from every pair and fixes it to some random value. And then we're going to get back this. So again, either you could think of this formula that we're proving the trade-offs for as the Satin formula with XOR substitution, or you just make 2 copies of every edge, call that graph G prime, and generate the Satin formula for that graph. It's exactly the same thing. Okay? So, but basically, we're going to mostly talk about the graph without double edges because we're going to do this whole trade-off plan, the progress and everything is we're going to define it for our original graph. Then we're going to take a proof for the multi-edge version of the Satin formula, and then we're going to hit it with a random restriction, and then we're going to be able to carry out this argument that we have the notion of progress. We're going to divide things up into epochs and then prove that every epoch cannot make too much progress, that since the space is small, you don't carry progress with you in between epochs, but you need to make a lot of progress. So then I need to tell you what the progress measure is. The progress measure is going to be the same we had in one of our very first lectures. So for a clause that is derived from a Satin formula, we're going to take the minimum edge, the minimum vertex at S, such that the parity constraints over S together imply the clause. Take any such S of minimal size, doesn't have to be unique necessarily, at least we don't know. Take the size of that, that's the complexity. Note that every clause has finite complexity at most number of vertices in the graph. Why is this? Well, because the formula is unsatisfiable. So if I throw in the whole Satin formula here, then it implies anything. In particular, in fact, the Satin formula, if you remove a single vertex constraint, then we're allowed to violate that vertex and can satisfy everything else. So the complexity of contradiction is exactly the number of vertices in the graph with this measure. which means that in order to refute the formula, we need to make substantial progress. We're starting off with very small progress because any axiom clause is implied by the parity constraint that it is a part of. So axioms have complexity 1, contradiction has complexity linear in the size of the formula, and then we have this sub-additivity, crucial thing that says that if I resolve C or X and D or not X to derive C or D, then the complexity cannot most double. Because if I take one set that implies this and another set that implies this, then their union clearly implies the result, since resolution is sum. Okay? This should hopefully be repetition. Now, just a piece of terminology. Let me say that if a set S implies the parities over set S implies C, and the S, there should be a C there also, and if it turns out that SC has the right size, then S sub C is actually witnessing that the complexity of C is size of S, and I will refer to S then as being a critical set. Again, it doesn't necessarily have to be unique, it is a critical set. Another notion is the boundary of such a vertex set. It is all the edges in the graph that has one endpoint inside S and one endpoint outside. And now there are two important facts. One we already saw when we did the Zetin lower bound. If S sub C is a critical set for C, and if E is an edge in the boundary, then the variable over the edge is in C. This I think we actually did. It's kind of a flipping argument. You do it by minimality. It is in the lecture notes. I'm not going to repeat it. So we did this before. One other thing that we're going to use is that, in fact, the set S is connected. Okay, let me do a very sort of hand-wavy argument for this. Here's the graph. Suppose it's not the case, and you know, here's a vertex, here's a clause C, and suppose now that we have S1 and we have S2, and they're not connected, and they together, I claim, witnesses the complexity of C. Since they're minimal, let me abuse notation a bit and just write, hopefully you understand, if I just write S1 for the parity constraints over S1, then we know by minimality that S1 does not imply the clause. I can satisfy all of these parities without satisfying C. I can also satisfy all of the parities over S2 without satisfying C. Right? Just because the definition of complexity, it's a minimal. It's a cardinality minimal set. But now if you think about this, the part of the assignment that satisfies S1 and S2, they're completely disjoint, precisely because these guys are connected. So then I can take, I basically just take the assignment to the S1 variables and the assignment to the S2 variables, and that joint assignment satisfies both of these, but still does not imply C. So any remaining variables now I just set them to falsify C, and now I have something that satisfies all of S and falsifies C, and that's a contradiction. That's basically how the proof goes. Is this believable? Okay, and we have our game plan, so I'm going to erase that now. Just to have it on the board, we are going to use the same restriction as last time. So rho is a random restriction, or really I'm describing the distribution over the random restriction. That basically it picks uniformly and independently at random one copy. Okay, that was hard to write. One copy E1 or E2 of every edge. Of every edge in in this G prime graph where we have 2 copies of every edge. And then fix this edge variable to a random value. Again, uniformly and independently at random. So if I start with a graph with double edges and a refutation of that, then I can just hit the formula with this random restriction, and that will recover the grid formula that we started with. And since restrictions preserve refutations, I will now have a refutation of this formula. What do we know about this refutation? Well, as we argued last time, wide clauses will disappear. Let me write that down. Or actually, let me not write that down because I'm getting a little bit ahead of myself. Let's go back to. It's always a good idea to follow your notes. So let me. So we have this random restriction. We're going to talk about it in a second. So let me set some parameters. T0. I'm going to set that to be W over 4. W raised to the power of 4. And now I'm going to say that C has medium complexity if the complexity of C is somewhere between T0 and say number of vertices in the graph divided by 4. What is that number of vertices in the graph divided by 4? That's WL divided by 4. And now you might worry whether this is actually larger than this. And it is, because W is strictly larger than 4 when I want it to be. Okay? And also W4, W raised to the power of 4 is smaller than that. So note that if you remember from before, we picked like basically, I don't even remember exactly where we picked, I think between all vertices and vertices half, or maybe between vertices half and vertices over 4 actually. Probably between vertices and vertices over half and vertices over 4. And we said that that's an interesting complexity. And when we wanted to prove state in lower bounds, we focused on formulas of that somewhat high, but not too high complexity. Now I'm going to be interested in many different complexities. All the different complexities I have between T0 and linear in B. How many? So let me define what a complexity level is. I say that a clause C has complexity level I, which is a natural number, if T0 times 2 to the I is strictly less than the complexity, which is less equal T0 times 2 to the I plus 1. How many complexity levels do we have? Well, we have roughly, just to get a sense, we have roughly log L different complexity levels. Okay. And note now, importantly, that before, if you remember the exponential state in lower bound, our argument was that, well, at some point in the proof, we're hitting a medium complex clause. But now what I'm doing is let me actually let this be the epochs, but let me now have like a, so let me have maybe time on this axis, and let me have complexity on this axis. Then basically I'm going to say this is the maximal complexity, like W over 4. This is maybe T0. So this is maybe, sorry, V over 4. This is maybe T0. And I have like a bunch of different, again, doing this log scale. I now have a bunch of complexity levels in between. And since I'm doing log scale, they're evenly spaced, right? And now you realize I'm starting out at time 0 with nothing, and I can download axioms. At the end, I have derived contradiction. During the proof, I'm hitting all of these different complexity levels. Because by subadditivity, there's no way I can skip a level. Are you with me on this? Like a very simple observation, but a crucial observation. So I have to hit all complexity levels. Okay, so now observation, any refutation of the grid formula has to hit all complexity levels. Okay. But now I want to argue that take a refutation of the G prime Satin formula. Okay. In small length and space. Okay. Now I want to argue, take such a refutation of the Satin formula with double edges. For such a refutation, it's going to be the case that if I sample a restriction like this at random, then it's fairly likely that then rho prime restricted by sigma is modulo relabeling. It's just a refutation of the standard Satin formula, except that it skips complexity levels. But that's impossible. That could not possibly be. So it could not have had small length and space. This is our plan. So what I want to prove now, so I will soon, we're going to use the complexity measure. That's going to be crucial. We're going to use the critical set, which is a vertex set that witnesses the complexity. We're going to use the definition of boundary, which are the outgoing edges from that set. We are going to use, crucially, that everything in the boundary, if S is a critical set for C, then everything in the boundary of S appears in C, and S is connected. Okay, so we should make sure to remember this, because this part of the board will very soon disappear. But let me tell you what the plan is. So in order to carry out this plan, we need to show, or we want to show, for say C1 and C2 of complexities I1, which is distinct from I2. So I1 and I2 are two complexities here. I want to prove two things. That when I sample with probability only over rho, note that the clauses are worst case. So with probability over rho, when I hit Ci with rho, the probability that I don't satisfy a medium complexity clause is going to be exponential in minus W, where W is this parameter. Why is this going to be? Well, because we already know from before that sort of all of these medium complexity clauses, I want to argue that they're wide. But now, so this is like one thing I want. I want another thing also, which would be great, because we're really gonna, at the end of the day, we're gonna have a union bounding argument, and we're going to look at different complexities and argue that at least some complexity disappear. And that is going to require a very tight control over the failure probability. In fact, so tight that we cannot, we want to argue that one of C1 and C2 is satisfied. And you can say, well, I mean, this is a great bound, and then we just argue by the union bound. We won't be able to afford that. In fact, we want to argue that this happens essentially independently. Okay, so we want to argue something like the following, that the probability that for both I1 and I2, the probability that both of these clauses survive, I want to say that that's going to be at most the product of the probability that one of the clauses survives. And in fact, not only do I want this for two clauses, I'm going to want this for like up to k clauses for some parameter k. Okay, am I making sense? So I want an independence result. What's the problem with that? Well, these two guys are coming from the same derivation, and they're actually probably going to be in the same configuration. They're highly, highly dependent. And yet this looks like I'm basically saying that how the restriction treats one of them is basically independent of how it treats the other one. That's just going to be downright false. Okay, so basically what I will need to do is, my setting is I will have a clause configuration, and I have clauses of different complexities, but they have been derived together. And now I want to argue that when I look at how the random restriction affects these clauses, we're basically observing independent events. Okay? That's what I want to prove. Is this making sense? And is it making it like this? Just has to be false, except we're going to make it true. Okay, so actually, I claim that we did this already last time. So formally, the claim, let me write it down as a lemma, and in the notes, this is now lemma 9. In general, I'm just going to make the claim that the probability for any clause C, that when I've hit it by rho, the probability that C restricted by rho has at least W variables is at most 3/4 raised to the power of W. Okay, we proved this last time. Let me just quickly recap why it's true. Well, let's look at the clause C before the restriction. If C before the restriction contained less than W variables, then we're kind of done. There's nothing to prove. So this event only happens if actually C before the restriction contained at least W variables. And now you can say, suppose that there's a case analysis. Basically, if C contains XE1, but not XE2, then rho satisfies C except with probability 3/4, which is a bad marker. Why is this? Well, rho is going to pick one of xc1 and xc2. So with probability half, it picks this variable, which appears with some sign in C. I don't know which, but I'm just flipping a coin and I'm setting x sub e1 to that value with probability a half. So with probability 1/4, this variable satisfies the clause. So it fails with probability 3/4. Okay. But if C contains both xe1 and xe2, then rho satisfies C except with probability a half, and that is smaller than 3/4 raised to the power of 2. Because in this case, we know that rho will pick one of these with probability 1, and it will set it to the right value to satisfy the clause with probability half. Okay, so this gives me exactly this. A simple corollary of this that will be important is the following, that now look at any clauses, C1 up to CK. And now I'm interested in what's the probability that all of them survive the random restriction, and afterwards, when I take the union of all their variables, it's a fairly large number. Well, that is going to be, so the probability that for all I, Ci restricted by rho is not satisfied. And when I look at Ci restricted by rho for all I in K, and the probability that it contains at least W variables, that probability is again 3/4 raised to the power of W. And the way to do it is that we'll take all of these clauses and concatenate them. Okay, firstly, if and then run this analysis, basically. It's like really the same. Are you happy with this? Okay. So, but now where I'm going is, what are these clauses going to be for us? These clauses are going to be from different complexity levels. And I want to argue that when you have K clauses of different complexity levels, first I want to argue that every clause is going to contribute W variables, essentially. But then, miraculously, when you take them together, because there are different complexities, in fact, I'm going to get a factor K in front, because they are of different complexity. So this means that if I have K clauses of different complexities and hit them with a random restriction, then the probability that at least one of them is satisfied and vanishes, it's going to be overwhelming. And that is going to get us close to this claim of independence, which is like false, except now it's going to be sufficiently true to get us what we want. Okay? So, so for this, I need some terminology. So look at the critical set S and look at the columns in the grid. For a fixed S, look at the column. I say that a column is full in S if it is completely contained in S. Okay, so maybe actually let me do it by picture. We're going to have full, we're going to have empty, and we're going to have partial. Let me do it by picture because I think it's easier. Let me draw an S. So note that S is a connected set. Here is S. Then these two columns are full. These two columns are full. These two columns are partial. So S contains some vertices from this column, but not all of them. Let's say this column, for instance, over here is empty. Okay, because it doesn't contain anything. Is the definition clear? So now I want to argue that if W4, which is T0, is less equal the size of S, is less equal size of V over 4, for any such set, the boundary of S has size at least W, where we have this W. Okay, what's the proof? Well, if we have W partial columns, then I claim we're done. Right? I mean, if we have W columns that are partial, then I'm going to pick up W vertical edges. So suppose that's not the case. If not, then we have S minus, so we have less than W partial columns. So clearly we have less than W times W vertices in partial columns. And the remainder has to be not in partial columns. So there are this many vertices in full columns, S minus W squared, which is W4 minus W squared, which is W squared times W squared minus 1, which is positive. So there is a full column. Somewhere in here, there is a full column. And now I just say that, well, since S is less than size of V over 4, at most a fraction 1 over 4 of the columns are full. Like a very crude bound. I'm basically ignoring, this is like the number of columns that S can mention. And now we said that less than a fraction W over L is partial. What is that fraction? Well, that's 1 over W3, which is as small as you like. So this means that, well, there's most a quarter of full columns, a vanishingly small fraction of partial columns, so there is an empty column. Okay, but now I've picked up a full column, say over here, and somewhere there's an empty column. So just walk. In every row, at some point, I cross the boundary. Okay. So then we have this. And note now that this means that I've actually taken care of this, right? Because now a medium complexity clause corresponds to a large boundary. And if the boundary of size W, then the clause contains at least W variables, but such a clause is quite unlikely to have survived the random restriction. I don't know, but it's a little bit confusing. We're going to switch back and forth between the XOR, like the multigraph and the standard graph, but most of the argument, we're only using the multigraph to get something which we can hit with the random restriction. So like all the complexity arguments are like in some sense after the random restriction. I don't know if I'm making sense.
So can you do them without the random restriction?
If we could do this argument without the random restriction, I mean, we could do some kind of embedding argument. It would still be no, it would still, yeah, it's a good question. I mean, in some sense, we know, I mean, I know that you don't need double edges, right? You should be able to, everything we do now, you can do in a grid, in a standard grid, but then you're just going to have a more complicated random restriction argument where you're going to embed this grid in a smaller grid, or you're going to embed, so the other way around, you're going to embed a smaller grid in this grid. This would be interesting to work out. This is somewhat similar to how the latest bounded at trigger lower bounds for the Satan and pigeonhole principal formulas use this idea. But there you have to work much harder. Okay, so here comes the punchline, and this is a point where I don't know how much suffering we want. So let me just tell you what is true. This is like a key lemma. I'm not sure if we will just accept it. So let's C1 up to Ck, and let me throw in that I think K is at most W. That will be a choice of parameters later. Suppose that there are clauses of distinct and increasing complexity levels. And now look at and let Si be a critical set for the clause Ci, importantly. And now look at the boundary of Si and take, in fact, the union of them. Then I claim that their boundaries, in fact, scale by Kw. And there is basically gonna be, okay, maybe let me hand wave the proof. This requires some careful argument, but let me not be careful. Firstly, let me just pick out every third clause in every third set. Why do I do this? Well, to know that they are the sizes of, well, after this filtering, then I know that the sizes are at least a factor of 4 apart. There's a lot of slack in this argument, but basically I could worry that, you know, the complexity of C1 and C2, they're different complexity levels, but their witnessing sets are like just off by 1 because they're right at the boundary. And I don't want that. I want like the S sets to be of very different sizes, so I just pick out every third if I need to. Okay, I still have like big omega of K. And now there's a special case. Suppose that there is an SI that contains W squared partial columns. Well, then we're already home because K is less than W. Okay, so like somehow if some set is very spread out, is very skinny, then we're already home. So this means that the only thing I need to look at is when sort of intuitively, all of the SI sets, they mostly consist of full columns. You can kind of ignore the partial columns, really. Just think of the interesting set is you're picking these SIs, and they're all just consisting of full columns. That's not true, you have to, but it's sort of morally true. Okay? And then it turns out that you need the following proposition. And this is, so let AI and BI be integer sequences so you should now think of as every SI just contains of full columns, and this is like the left and right side of where the full columns and start and stop for SI. Okay? And what do I know? Well, I know that all SI, all BI, all endpoints are like apart. And that is because the sets are somewhat large. I mean, they don't fit in a single column, right? All sets have size at least W to the power of 4. So this is definitely true. But I also know that because the SI sets are so different, remember that their sizes differ by a factor of 2. So even when you take care of the partial columns and you throw them in, then it's going to be the case that the endpoints corresponding to SI plus 1 are 2 times further apart than the endpoints corresponding to SI. So basically, again, because we are in a full column setting, you can just simplify this to a line. And basically, I'm asking you now to place out k intervals, but they're of doubling sizes. So here it's like, the first interval is somewhere here. And now the second interval has, I didn't state what holds. So suppose that this holds, then the punchline. I take the union of all the AIs and BIs, where I goes from 1 to k. That is at least k plus 1. So basically, I'm saying if you pick out, so here's the smallest interval. Here's the next one, which I maybe place here. Then the next one has double the size of the blue one. So maybe I'll place it, here. And then comes a red one. And that is double the size of the green one. So maybe I place it, here. The point is that, and now I collect all of these endpoints. And I'm saying there's no way you can pack this together to avoid, like, every new interval is going to provide one new endpoint. This is what this says. Do you understand? Okay. Now this requires an argument. But if you're buying this argument, and if you're buying that there are few partial columns, then I basically take this and just pull the grid apart, and now I pick up this plus a factor W. And then we have this. I'm cheating you on quite a few details here, but like morally, this is why it's true. And the notes are not cheating you, so you will see all of this in the notes, hopefully. So that means that now, if you believe this, we're getting close to, I'll try to get to a point where we can state at least one trade-off, and where you can believe that we would have gotten this trade-off. So now, importantly, I say the following. For any set of clauses, M, so note now what this tells me. Again, this tells me that clauses of different complexity levels have critical sets of very different size. Their boundaries collectively are going to be very large. But this means that this is the number of variables, at least collectively, in all of these. Okay? And because this is so large, when I hit this with a random restriction, at least one of these CIs is going to be satisfied, definitely. Okay. And again, I could try to argue via union barn argument, but that would be way too weak. I really need to pick up this factor K. Yeah. So from this, it follows, if you look at any set of clauses M, the probability after hitting with a random restriction that this set has K distinct complexity levels that's going to be size of M times some C raised to the power of W raised to the power of K. For some C that lies between 3/4 and strictly bounded away from 1. In fact, I can get 3/4, but we're not going to kill ourselves today. Okay. Basically, we have this, remember this, we said that, well, if a single clause has width W, then it gets satisfied with probability, it survives only with probability 3/4 over W. And then we have this corollary that says that look at a bunch of clauses, the probability that they all survive and afterward contains many variables was scaling in the same way. So for any K subset of M, the probability of that set that we have K distinct levels, if we have distinct levels, then in particular we have this many distinct clauses, but that is unlikely. In fact, that probability is at most 3/4 raised to big omega of KW. And now we actually know the parameter in here. The parameter in here is, it's not something ridiculous. It's going to be like a third or something like this. And therefore you can work on this. But let's just say that this is smaller than 3 times KW for some C that is at most 1. Okay, and now we just say how many subsets do we have? This many, right? So M, size of M choose K. Well, that's at most M, size of M to the K. And now just by a union bound, we see that the probability that I can pick out some K subset from M such that clauses of K distinct levels survive is going to be, the union bound gives me all K subsets times the probability of a single set of surviving. And now I get M times C raised to the power of W raised to the K. Okay, and now we're almost done, at least with the cheating version. So now what I'm going to do is, here's the proof. Here's the proof. I've divided it up into M epochs. Here is the maximum complexity level. So up here somewhere we have contradiction. Down here we have like the axioms. And now I'm going to look at one of two things had better happen. Either at some of the breakpoints, like either at this point in time, or this point in time, or this point in time, or this point in time, there is some medium complexity clause. Right? There has to be some medium complexity clause here. Or else, what if that is not true? What if there are no medium complexity clauses here? Well, in that case, there is some epoch where you make the jump from all of the clauses being down here to all of them being up here. Right? So this is like the border of, you have to be clear, this is the upper and lower border of medium complexity in S. Okay? And I'm saying that either at some breakpoint you're inside here, or during some epoch you take the jump from here to here. But if during some epoch you take the jump, you're hitting all of these levels, right? Now we want to argue that this is not unapplied. Okay, let's see if we can get this to work. So we have two events. Events E1 is there exists a medium complexity clause at some breakpoint. Event 2 is some epoch has clauses of all complexity levels. With probability one of these two events will happen. Let's see if we can understand what the probability is. So again, we have number of epochs is m. The proof length is capital L. The proof space, clause space, just to avoid confusing ourselves, let's say that's lowercase s, because uppercase s is usually size for me. Then, well, a medium complex clause survives. So let's actually, a medium complexity clause, if C is medium complexity, we know that the probability over rho that C rho is different from is not satisfied, that was at most 3/4 of raised to the power of W, right? So union bounding we say that the probability of E1 is at most, how many breakpoints do we have? We have m breakpoints. We have at most s clauses at every breakpoint. So this is where I'm using limited space. Times 3/4 over W. Okay, so if m is not too large and if the space is not too large, the idea is that they're going to be killed by this exponential. Are you with me so far? Okay, so the second point is now we have to have one epoch here, maybe, where we hit everything. Okay, so let's see if we can figure out why this is unlikely. So this was E1. Let's do E2. So there are K O log L complexity levels. There are L maximum LM clauses derived in an epoch. Note that I already took care of the breakpoint, so now I'm only looking at the new clauses that appear here. So this means that we have at most L over M candidates for medium complexity clauses. Okay, but now we're going to use this lemma, right? This is our M. So now we get something like that the probability of E2, let's see if I can get it right, is going to be something like, So for a given epoch, I get L over M, that's the size of M, times C to the W raised to the power of K. And how many epochs do I have? M, right? So let's see. So this expression and this expression. And now I'm just going to, what I can do now is I can play with my parameters. I've used all my lemmas. So now what I'm going to do is, we know that MS actually C to the W, let me just weaken this a little bound. This probability plus M L over M C to the W raised to the power of K is 1, right? Because one of the event happens with probability 0. Now just fix M. I can play with this. This is a number of epochs. Let this be 1 over 2 times the space bound times this whatever constant C that I pick up raised to the power of W. Then you see that this is just going to be a half. I'm doing something pretty stupid. I'm just fixing this to a half. Well, I mean, I want these probabilities to be the same. So I'm not so stupid maybe. So I'm fixing this to a half, and now we get that, well, in that case, we get that 1/2 is at most M times L over M times C to the W raised to the power of K. And now I'm getting a little bit lazy. Now plug in M. So this is like 1 over 2 SC to the W. And now I pick up 2 times L times S times C to the W times C to the W K. And now if we relax a little bit, we get something like that length times space is then, well, raised to the power of K. Let's ignore this. Then that's going to be basically something like 1/2 times 1 over C raised to 2WK. That's this guy, right? I'm just shifting this over to the other side. Okay, and I'm ignoring this just because, I don't know, it's getting late. So now I see that length times space has to be, let me ignore this factor a half also, and let me get rid of the case. Then 1 over C raised to the 2W. So length times space is at least this. Note that this is, we have something somewhat grow large here. And C is less than 1, so this is larger than 1. So this is some kind of exponential. Length times space is exponential in W. So this is already something. This is not what we're shooting for, but this is something. Now, what I would do is, so basically what we did, well, let me tell you very briefly what we're going to do if we really want to squeeze the juice out of this. So here you have your epochs again, 1, 2, 3. Suppose that M is equal to 5. Then basically, if you really want to optimize, you are going to say, well, you're going to identify. So one reason that we're not optimizing, if you see it, like here for E2, we're using this super powerful lemma, but for E1, we were just using a standard stupid union bound. So we'll set parameters slightly differently so that we'll just force, if we don't have complex clauses at the boundary, then we have some epoch where we make a lot of progress. Okay, but then we're just going to split all of these epochs apart, and in the epoch where we make a lot of progress, I don't know which one of them it is, but I'm going to split all of these also into M sub-epochs. And I'm going to say that, well, if in one of these epochs I make a lot of progress, now let's suppose it's in this one, then we zoom in and say, well, here also we're making a lot of progress. Okay, and if we're making a lot of progress here, then we're actually going to find like, oh, in this sub-epoch, we're making a lot of progress. And now we're going to actually, for all of these, we're going to split them up into sub-epochs. And to some recursive depth. And then we're going to argue about basically, we're going to have a lot of different breakpoints. And now we're going to say, okay, suppose that at some of these breakpoints, we see a lot of complexity levels. That's going to be somewhat unlikely and now we're going to take the same, so we have like a new event E1 where we actually can take this powerful lemma and say that with some probability, we're not seeing too many complexity levels at all of these breakpoints. And then the event 2 is that somewhere deep down, we find a sub-epoch that is making a lot of progress. And now we carefully tune parameters, which I think you will have in the scribe notes, because it's already there. If you now tune the parameters correctly, then what you're going to get is what I stated. But if you understood just this one level of epochs and breakpoints, again, you do get something. I mean, this is already some kind of trade-off. And hopefully, like you saw all the ingredients. I mean, you saw the epochs, you saw the breakpoints, and then very importantly, you saw the extended isoperimetric lemma that had the property that if I have a graph, like the isoperimetric property is, if I'm just saying I have one medium-large set, it has a large boundary. The extended isoperimetric property is, suppose I have several sets of medium size, but their sizes differ by factors of 2, say, and I take the union of their boundaries. Then they should pick up also a factor which scales with the number of sets. And this is, we hand wave the proof, but this is like an important technical part of the proof that you really have to prove. And I only sort of, I told you morally why it's supposed to be true, but we didn't really do the proof. So now I think we're leaving size space trade-offs behind for resolution for polynomial calculus. We will talk a little bit about trade-offs in cutting planes, but that's going to be in 2026. And it turns out then you need completely different techniques, although we're going to go back to pebbling formula. So again, the open problems for now, we didn't even talk about PCR, polynomial calculus with dual variables. That proof is very complicated. It would be nice to clean it up. It would be nice to do something that is independent of the characteristic. These parameters are not good in the sense that we know that you can do something better for regular resolution. Also note that the blow up that we got was something like, I mean, the size blow up looked like something like length to, again, log n divided by log. So we're not getting an exponential blow up, just something quasi-polynomial. It would be nice to get something truly exponential, but then you need another formula. Like these, the upper bounds that we did prove that you cannot get like something truly exponential out of these formulas. It's just not true. So there are lots of questions here how we could tighten the screws and make this nicer. Again, as I said, one nice thing would be to do this for 4 CNF formulas. That would require an embedding argument where we would take a smaller grid and embed it in a larger grid and then use a restriction argument for that. If you really want to optimize parameters, you should, of course, do it for 3 CNFs. We know for 2 CNFs, you could not possibly do it, but getting these kind of trade-offs for 3 CNFs would prove that, again, there's a sharp, like, sharp phase transition, if you wish, when you go from 2 CNFs to 3 CNFs. It's kind of clear you should do, for 3 CNFs, you should do this, but you should do it on hexagonal grids It can probably be done. It's a little bit painful. Yeah, so the final lecture, what are we going to do on Thursday? We are going to go back to space and look at polynomial calculus space in isolation. For resolution, we said that, well, we sort of, if we understood width and got lower bounds, then we could get almost all space lower bounds, except that it didn't work for pebbling formulas, so that we had to lift pebbling lower bounds. And that sort of tells us for space and the relation between space and other closed space and other measures in resolution, we know almost everything. I mean, maybe there are room for some improvements, but we have a pretty good picture. For monomial space in polynomial calculus, that's very much not true. And in particular, the space lower bounds are way more complicated. And we're going to see next time how to prove space lower bounds for random KCNF formulas. And then once we reconvene in 2026, we're going to talk about whether monomial space and degree is related in the same way as closed space and width are. And this is also open. So there's a lot of open problems regarding polynomial calculus, questions related to space, lots of room for getting a better understanding and improving your results. Any questions before we call it a day? And let us call it a day.